And so also for gravitational waves from after the merger. Yeah, and the way, so the way to really simulate the instabilities is using some realistic resistivity, because resistivity would cut the amplification at some point. While in our simulations, it currently is only cut by lack of resolution. It's only cut by lack of resolution. Okay? So even we cannot use high resolutions because we already use the largest computers available, and we can only do that much on one hand. On the other hand, even if we have bigger computers, we will see further growth of instability, but at some point there will be invisible, because there is some physical resistance, resistivity that stops the instabilities. And so this is a very open problem, and that's actually what I would like to talk in my last slide. As a summary of these lectures, I show again the fundamental equations that hope you learn how to solve: Einstein equation, matter equations, equation of state, and also Maxwell equations. And actually that's not all. There's more in nature, and we're starting to do that. We have to simulate neutrinos in our neutron star binaries or similar supernova explosion and so on. We have to simulate radiation transport. We have to simulate nuclear decays, because the neutrons or neutron stars, when they go outside the star, they decay. They form, they decay as neutrons, free neutrons, or they decay by forming nuclei, heavy nuclei. That's a very lively field of research nowadays. And we've been using perfect fluid, single fluid all the time, but maybe protons and neutrons have different flow properties in the star. We may need moving fluids. And the crust of the stars is probably solid. And of course, we not yet any clue how to simulate that. Okay, so these are some of the most open problems, unsolved problems, and on top of the magnetic instability problem. And and on top of all this, we need to do with high order, higher accuracy numerical methods, and to be able to run our codes fast enough to explore parameter space, so that when the observations of binary neutron stars through gravitational waves happen, we can run our code in a few hours and tell you what was the source that generated them. That's for the far future of you young students. Okay, I think I can conclude here. If you don't have any questions? Questions?
How about the Newton star?
Okay. So yeah, this is also very active field of research. It's been very active for a while. The ones I showed you are the simplest equational state, monotonic equational state, and the equational state. We are using equational states coming from nuclear physicists that try to create them from theory or from some phenomenology, of which I'm not such an expert. So we do different simulations using different equational states and try to see what are the differences. We try to predict what would be the different gravitational waveforms from stars with different equations of state, so that when we have detections, we can say something about what was possibly the equational state of the stars. So yeah, it's very active field of research that can either use tabulated equations of state received from the nuclear physicists, or what most often happens is that we take tabulated equation of state, we fit them with piecewise polytropes, we add some thermal part to allow for shocks and entropy variations, and we use them in our code because they're much faster. They're a good approximation of the nuclear equations of state, but they're much faster.
So we can use the same framework to simulate galaxy reports.
The collapse of a neutron star to a black hole?
Yes.
Yeah, sure. That's something I've been doing for my PhD thesis, for example. Yes? Or even in supernova collapse. When supernova collapse, Einstein took it as is fit to simulate the high density of the core collapse. It's you need some different types of codes to be able to simulate hundreds of kilometers of matter that you need for the outflows of the neutron. The core collapse is really studied also.
But I wonder how do you avoid the errors?
Right, that's through the gauge.
Okay.
Yeah.
The same strategy used for the vacuum case.
Oh yes, it's exactly the same. The gauge is actually the same.
So could you comment on the simulation on the extremely mass ratio?
Okay. Yeah, extreme so one medium mass black hole and one solar mass black hole. Yeah, so this is something you cannot do directly with the Einstein theory or with finite Greek codes because the scales are too different. The mesh refinement is not enough to go to this extreme mass ratio. We can go to some mass ratio. I don't remember, it's been done, I don't remember, maybe like 30 to 1, 50 to 1, something like that. I think it's been done. Not here.
Okay. No further questions? Thanks.